And because we're oxidizing this from an alcohol to a keto group, we can basically capture those high energy electrons as an NADH. All right, so that's the second CO2 we've lost. We lost one in the pyruvate dehydrogenase reaction, in the making of acetyl-CoA. Now we've lost that one too. Oh, this molecule down here is alpha ketoglutarate.
Do we need to know the enzyme?
What's that?
Enzyme?
Oh, the enzyme, thank you, is isocitrate dehydrogenase. Now I'm going to draw the structure of alpha ketoglutarate out again over here. To point some similarities between the structure of alpha ketoglutarate and pyruvate. So if we draw the structure of alpha ketoglutarate, that's another way of drawing the structure of alpha ketoglutarate. 1, 2, 3, 4, 5, yeah. So this is alpha ketoglutarate. So let's compare that to the structure of pyruvate. Both of these are what you would call alpha keto acids. So there's a keto group at the alpha carbon from a carboxylic acid. I mean, we could think of this, we could put R, in here case R is a methyl group, here the R is the CH2CH2COO kind of thing, right? The reason I wanted to point this out is because in the pyruvate dehydrogenase reaction, we took the pyruvate and we decarboxylated. So again, this is the PDH reaction. And we decarboxylated, we brought in coenzyme A, we made NAD and we made NADH. And we ended up with acetyl-CoA as our product. So basically, this next step in the citric acid cycle is a very analogous reaction to the pyruvate dehydrogenase reaction. Except it's known as alpha ketoglutarate dehydrogenase, and it does the same kind of thing. And it has the E1, E2, E3, and all those different cofactors, and the whole, it's a great big complex. All right, so this is alpha ketoglutarate dehydrogenase. And so we're going to get rid of a CO2. We are going to bring in the coenzyme A. We are going to take NAD and we're going to make NADH. Except now the coenzyme A, instead of just being a methyl group, carbonyl and coenzyme A, it's going to be all this other stuff. O minus CH2, CH2, C double bond O, S CoA. But it's basically the same reaction. And this product is known as succinyl-CoA. So
So I have a question.
Yeah.
So is the alpha ketoglutamate going to the one that you just drew, or is it going to the pyruvate?
No, this, I just wanted to kind of show the parallels between these reactions.
Oh,
That
okay.
basically, so the pyruvate dehydrogenase reaction sequence,
Oh, that's separate.
that's separate,
Gotcha.
but this alpha keto is basically the same reaction, except it just has a different R group in here.
Oh, okay.
And so again, structurally it's the same and everything like this. And so that now when we come down here to our cycle here, we can do the same thing. We can bring in coenzyme A. We're going to get rid of carbon dioxide, and we're going to take NAD. We're going to make an NADH plus H plus, and we're going to generate succinyl CoA. In there. And now we've gotten rid of our last CO2, right? Our 3 CO2s. And remember, per glucose, we generate, 2 pyruvates, right? So per glucose, all this happens twice. So by the time we got rid of a CO2 and pyruvate dehydrogenase, we got rid of a CO2 and isocitrate dehydrogenase, and we got rid of CO2 in alpha ketoglutarate dehydrogenase. We've gotten rid of all the CO2s, because you do that twice, that's 6 carbons, right? You do that twice, that's 6 carbons. So, like I said, now we can exhale, right? We're going to get rid of the CO2, because we've gone through and we're getting rid of all the CO2 that we generated from the oxidation of glucose. I'm going to go ahead and stop there, and right in the middle of the cycle, but that's okay. We'll come back, we'll kind of review this a little bit at the beginning of next time, and then we'll finish the cycle. The rest of the cycle is going to be basically taking these carbons, reconverting the oxaloacetate. We get another NADH out of that process, and an FADH2 as well out of that process. But we'll finish that up on tomorrow morning.